Wait a second. Hang on a second here. Just want to make sure. Oh shoot. I can record. Sign in. What is this? Huh? What is this? Well, why is it that when I click on it, enter the letters, it closes it? Okay, what is this? Poutsable. Poutsable. It's not even, huh?
You can just type it.
What do we do?
You can type it.
Yeah. Oh, okay.
Probably just,
Yeah, but why would it?
previously entered.
Okay. All right, signed in, signed in. Is that me? Okay. All right, good. 10-kilogram box pulled to the right with a force of 40 at an angle of 30. What's your picture gonna look like? So always start with your free body diagram, okay? So this is the 30 degrees going this way. This is the applied force, okay? It says, assuming there's no friction present, calculate the acceleration of the box. Okay, so what other forces are acting here? You know that there's gonna be Fg, and the table is gonna push up on it, so you've got Fn. And if it is moving, it says calculate the acceleration. So I'm gonna add a force here, and we can call it the net force. Now, do you remember when we add the net force? The net force is when the motion. Oh, did you get the whiteboards? Yay! So this is the motion of this object, and it is moving along. Thank you, John. It is moving only along the horizontal. Okay, so even though you're lifting it a little bit, it's not leaving that surface, right? Okay, so calculate the acceleration of the box. So let's figure out what we need to know. A, which means it is part of the net force equals MA. Okay? So remember, this is the second law of Newton. Do we remember this, the laws of Newton? The laws of motion? Okay, this is the formula for the first, the second law of Newton. The first one is just inertia, right? And then the third law is action and reaction. Okay? I think I'm going to give you a handout on that, the one that I would give the 30S, but that's just a review. So this is the net force. Net force is MA, and we're looking for that. So if there's no other force involved, what forces are in the X component? Can you first give me what are the forces acting on the Y component? Yeah, there is FAY here. And there's also FAX, right? So let's just do the Y component first. So the net force on the Y, what do we have? FAY. That's going up, so that's plus F of N minus Fg equals 0. So it's a state of static equilibrium. This is a dynamic equilibrium. Why do we know this is dynamic equilibrium? It's moving, right? Still at equilibrium, even though it's moving. So, is this okay? Do you find the writing equation okay? So you just look at the picture. You know that they're both up, so you add them, and the Fg is down, so you subtract it. Now with the X component, what are the forces in the X? So net force is Fa of X, which is positive, right? Remember, net force is always positive. which means FA of x that goes with the positive will have to be positive then. And is there any force that's opposing the FA of x? No, because frictional force is equal to 0. No friction, it says there, right? So if we're looking for the net force, which is the acceleration, net force is m times a, that is just FAX, isn't it? And how do you find FAX? The force is 40, applied force is 40 newtons. Cosine of 30 divided by the mass of 10. And that will give you the acceleration. Okay? So just to kind of give you the step that's missing here, this will become FA cos theta. This is going to be divided by m, divided by m. Right? See, the m disappears. So this will be divided by the mass, which is 10 kilograms. And you will get your answer. That should be it. Right, let's just double check what you have. Cosine of 30 times 40 divided by 10. And you have 3.46 meters per second squared. Now, just to double check, before I put this final answer in a box, I'm going to check for significant figures now. Okay? How many sig figs should we have for the magnitude? Look at the numbers given. It says 10.0. How many sig figs is that? You have 3 sig figs there, and then you got 40.0, 3 sig figs again. The angle is a separate entity, so we don't combine angle and magnitude. In this case, you don't need to have the angle. So the acceleration should have 3 sig figs here, so 3.46, and you know it's just going to go forward that way, right? But we know that. So you can actually just leave it just with the magnitude. Here you go, going forward to the right. That makes sense? Okay? So you see, once you know how to do, again, the strategy, what are the strategies? Start with the free body diagram. Free body diagram. That's the first thing you do, is put all the forces possible. Once you have them all labeled, right? Label the forces. Label all possible forces. Okay? If you have angles, you're going to have to split this into x and y. If you have angles, you need to figure out if you have split it into x and y. And then number 3, you may have to unite x and y by finding the common ground, like what we did yesterday. That's what we did. We'll do more of that, uniting the x and y. Okay? I want you to try example 3 on your own to start, just to get you started here. Okay? So example 3, the free body diagram, start with that. Again, this is frictionless. Okay, so you already have the FBD, that's your step 1, and you have an angle. So your next step, so where would you put the net force? I just want to get you going in the right direction here. Where would the net force be? Well, figure out, where is this backpack moving? Is it moving? Well, let's take a look at the graph. Is the graph moving? Right, does this indicate there's motion here? It is, right? How is so you know that it's moving because the velocity is increasing as time goes on. It's not zero. In order for this to be stationary, the v has to be zero, flat line at the 0 meters per second. So we know it's moving. How is it moving? Is this accelerating, decelerating, or constant velocity? Look at the number, it's increasing. So this is accelerating. There is an acceleration here. Is this a positive or a negative acceleration? Is it speeding up in the right direction? Yeah, it's a positive acceleration, right? Okay, so if the applied force is to the right, the direction to the right, where would you put the net force? If you pull your bag to the right, where would the bag move? To the right. So you're going to have to add this is your net force. So we need to add that in our free body diagram. And what is the sign of the net force? It's always positive. Okay, what else is not on the picture yet? What other forces are here? You got your applied. I'm going to just extend this and so it's easier to see. There's the applied and you have your Fa of x and Fa of y. Okay? So now I want you to go one step ahead and write down the x component forces. What are the forces in the x component? So you'll go net force on the x. What do we have there? And what are the net forces on the y? And as you can see, it is exactly the same as the previous question. This time you're looking for the applied force. So we're looking for the Fa. So where's Fa? Fa is right here, right? Fa is also there. So we're looking for the Fa, not just x and y. So this is your net force is Ma. Net is always Ma. So Ma is equal to Fa cosine of theta. So now we can actually start putting the numbers in here. Okay, do we know the mass? Yes, we know the mass, 2 kilograms. What about the acceleration? How do you calculate the acceleration? This is again going back to 30S physics. You have a graph. Okay, what's acceleration? Can somebody define acceleration for me? Change in velocity over time. What does change mean? V2 minus V1 over, in this case, T2 minus T1. Okay, so you need to calculate the acceleration from the graph. And how do we do that? Slope. That's what slope is, rise over run, right? So I'm going to go all the way to the very top. So this is 2 right here. 2 minus 0, it started at 0, divided by 16 minus 0. I think that goes to 16. So what's 2 divided by 16? You have 0.125 meters per second squared, right? So now we just found our acceleration. And so then you can figure out your net force, right? So your acceleration is 0.125 is equal to Fa cos theta. Now I'm just going to isolate the Fa because we know the angle is 30 degrees, and that's going to give you the Fa. This is the Fa, right? And look at that, we didn't even need the y component because we're just looking for the Fa. Because Fa of x is Fa cos theta, and you know the angle. That's it. That gives us everything we need. So 2 times 0.125 divided by cosine of 30. You're on degree mode. So the FA, is that right? 2 times 0.125 divided by 30 is 0.2. How many sig figs? Only one sig fig because of the 2 kilogram. 2, 8, 9, so 0.3 newtons. Yeah. And why is the FA so small? Again, you look at your numbers and you go, what? That's it? 0.3 newtons? Why is it so small? Well, first of all, mass is 2 kilograms, not that much. But the more important thing is that the friction is 0. As a matter of fact, if there is no friction, let's say you actually can have a grip. You're standing and you can have a grip to actually pull something, right? You are able to move anything. Doesn't matter how heavy that is. So let's say I'm standing here and my feet are actually able to, here's the question, I'm gonna put a frozen lake. This is a frozen lake from here to here. This is a frozen lake where friction is 0, okay? If I'm standing right here and you have a box right there and I pull it, do you think I'd be able to pull it towards me? Yes, you can, but you know what's gonna happen? I'll move too, because there is no friction that is holding me to that ground. If I apply a whatever force, once I pull it towards me, I will actually move to it as well. There's no friction. So friction is only determined by the mass. But if there's no friction, it doesn't matter what mass the object has. You see your desk? Okay? Can you push your desk with one pinky? Go ahead, try your one pinky and just push it. Can you move it with one pinky? Can you? Why? What's the answer to that? You're gonna tell me because it's heavy? The real physics answer to that is because the force that you're applying is not enough to beat the friction between the table and the floor. Now imagine your table, the bottom of the legs of that table is touching the floor, which has 0 friction. Okay, and let's assume that your feet and the floor actually have friction, and all it is there's no friction where the table and the floor is. You can actually push that filing cabinet with a pinky because there is no friction. There's nothing to hold that mass down. So you can actually push it very easily. It's the friction that is making it harder to move the object. Okay? So the friction, the applied force is so small. That's the reason there. Mass is small, 2 kilograms only, and the frictional force is 0. So this is why the applied force that you need is small. Make sense? So you kind of have to make a connection between what number you're getting and does that make sense? Okay? Okay, shall we continue? I'm gonna do all the examples, okay? This time you now have friction. So let's keep going with the examples because you have 6 questions to do then at the end of this lesson, right? And then the lesson is done. And then you have inclined planes for lesson 3. So I'm gonna do a couple more here and then we're gonna move on to lesson 3, okay? All right, example 4. You have a box pulled at a constant speed of 0.4 across a frictional surface. So there's your applied force. You're looking at the values for the blanks. Okay, so what do we not know here? All right. Okay, so you know that the mass is 20. How can you calculate the gravitational force from that? Mass times 9.8. Okay. Once you know your gravitational force, you'd be able to find the net force. Now, before you, okay, I'll let you finish that. Finish writing that off first. Okay, so you have 196 newtons, right? Is the normal force equal to the gravitational force? No, why not? Because you're lifting it a little bit. Even though it didn't leave the floor, you lifted it a little bit with your applied force. So the invisible force that is not shown on the FBD would be this. You got FAY and FAX. And did it actually move? It says constant speed. What does that mean, constant speed? Acceleration is 0. And if net force is m times a, then the net force is also 0, because you know what? It doesn't matter how much mass you have. If your acceleration is 0, the net force is 0. And again, that tells you, doesn't matter how much mass you have, you don't even need to apply a lot of force to push an object if there's no friction, right? Okay, so how do we find the Fn? Right here. You're looking for Fn. So can you go and find Fn? How do you find that? Do we know the applied force? Applied force is 80 newtons, right? So the blanks that we need to figure out are, you need to find your Fg, done. We need to find Fn. We need to find friction and mu. So we need 4 things in this question. So we got the Fg. We have to find the Fn, but first we need to find this. How do we find the Fa of y? Fa sine theta. Okay, so Fa is 80, sine of 45. All right, what's that? 56.57. So I won't round off now to sig figs. I'll just leave it. So there's your Fay. Fg is 196. Take away the Fay, 56.57. That's going to give you your normal force. And this is 139.43. Does that make sense? And I'm not worried about sig figs. Is that the end of the... so the normal force is one of the blanks. And I need to have how many sig figs? Take a look. How many sig figs in 0.40? 2 sig figs, right? So I'm going to leave this to 140 newtons. So we got Fn of 140. Fay, we don't really need to look for. So this is just a stepping stone to find that. So we're done with normal force, 140 here. Okay, gravitational force, 196. And then, so one last thing, we need to find frictional force. You remember how what the formula is for frictional force? Mu F of n. Once you know, oh, we don't have the mu. We don't have the mu, so let's find the mu first. So we can't go straight and finding frictional force, right? Okay, so we actually need to figure out the components in the horizontal direction, right? So let's start by putting the net force equation down for the x. So what are the net forces on the x? Fax minus frictional force. Why would I put 0 right here? Acceleration is 0, that's what we were told, so net force is 0 as well. So that means Fax is equal to frictional force. Okay, now remember, we can't use the mu F of n here, so we have to go with the Fax being Fa cos theta. So that had to be the way it's done. So Fa is 80 cos of 45, and that's gonna be, oh, you guys are quick, 56. Yes, that's right. We actually did calculate that already. So 56.57 Newton because of the 45 degrees. That would have saved you 1 minute there. So we know that this is the FA of X, which is the same as FA of Y. Done. So the frictional force is 50, I'm gonna just write down 57 because of the 2 sig figs. So 57 Newton goes there. So we got one more to do. And I think you know how to do the last one. Frictional force is equal to mu F of N, and you're solving for mu. So frictional force divided by F of N. So what's our frictional force again? 57 divided by 140. It's been rounded off. So the answer is 0.40 mu. There you go. And that completes the blanks. Okay, so what I'm gonna do is I'm gonna leave you some time to do example 5, and I'll show you. Actually, you know what? Let's go to example 5. Let's go to example 6. I want you to do example 6. It's a little bit different. The strategy is the same, so you just need to show the strategy now, and then we're gonna go right into lesson 3. Okay, and then we're done. So we should have some work time today and tomorrow. Okay, so try example 6, moving on to example 6. And I want you to try it on your own. Very similar to example 4. So that would be, where's 196? Oh yeah, we didn't take that into 190. But this will be converted to 200, but 200 only has 1 sig fig. So the only way you could do this to 2 sig fig is 2.0 times 10 to the power of 2 Newton. So that's what you would put in the box. Good question there. Yeah. There. Yeah. Because 196 has 3 sig figs.